Okay, we're going to look at two different sets of control charts. The first set is called variable control chart, and then there is attribute control chart. The variable control chart, they come as a pair. Okay, and those are X bar chart and R chart. X bar is for the mean of the production process. R chart is for the variability. Okay, and these two come as pairs. So any variable that you want to control, then you will prepare two charts for each of those variables. So for example, if let's take a very simple example of a coffee production process. So you have a coffee machine that produces coffee, and you may have several variables relating that to that coffee. Maybe there is temperature there, and there is consistency, and there is level of coffeeness or whatever. So there may be several variables that you may want to monitor, and for each of those variables that you want to monitor, you will prepare two charts, one X bar chart and one R chart. So when you do that, then you have two stages. One is, the first step is to develop the chart itself, meaning the levels, the upper and lower control limits within which the process is supposed to operate if it has only natural causes. Okay, but if the value strays outside these control limits, then you suspect assignable cause variability, right? So two stages. First stage, you have to develop the control limits, the lower and the upper control limits. Then once you have developed that, then you apply it in production on a regular basis and use it to monitor the production process. Developing the control chart and then using the control chart to monitor the process. And these control limits that we are going to develop relies on central limit theorem. Central limit theorem says that whatever the underlying distribution, probability distribution in the production process may be, if you look at the mean value, and the mean will follow normal distribution, approximately normal, right? And that approximation becomes closer and closer to the actual normal distribution as the sample size increases. So that's the reason in statistics sometimes they use n equal to 30. But in fact, if the distribution is kind of uniform or somewhat similar, then even for small sample sizes like 3 or 4 or 5 even, the X bar will exhibit normal distribution properties. So we really can make use of that concept here. So what we do is, what does the central limit theorem say? Central limit theorem says if you take these samples and find the sample mean, that sample mean will have the same mean as the production process from which the sample was taken. Also, that the standard deviation of that sample mean will be sigma over square root of n, the sigma of the production process divided by square root of n. Now with this, we can set up a okay, so here is the central limit theorem distribution, and you see that if you develop a 3 standard deviation interval, 3 standard deviation of X bar. So here is the mean. So if you go 3 times sigma over square root of n, then 3 times sigma over square root of n. Okay, sigma over square root of n is the sigma of X bar. So if you go 3 standard errors of the X bar in either direction, that you get an interval within which 99.7% of X bars will fall. So if X bar falls outside these two limits, then it may still be a valid X bar, but that probability is 0.3%, very, very small. And therefore, you should suspect that maybe there is some assignable cause variability due to which the X bar is actually falling outside the plus or minus 3 sigma limits. But if you do 2 sigma of sub X bar, that would cover. So if you go 2 sigma sub X bar, 2 sigma sub X bar, that will cover 95.5%. So which means we can set up limits in this fashion. If you want 99.7%, then you go plus or minus 3 sigma sub x bar, where z is 3. If you want 95.5%, then 2 sigma sub x bar is sufficient. So usually 99.7% is more common, okay, 3 sigma limits. All right, so here is the formula for setting up the control limits. So this is how this will work. So you take x bar, okay, you take a sample, okay, find the x bar. So you take another sample, find the x bar. Take another sample in equal intervals. So for example, if you're running a production process on an 8-hour shift, you may want to take one sample every 15 minutes. So this is the first stage. Remember, we are now trying to develop the control limits. So every 15 minutes, each sample is pretty small, say 5 or 4 or 3 or something like that. But you repeat the sampling many times, maybe 20 times, 30 times, 40 times. Okay. Then you compute for each sample, you compute an x bar, and then find the mean of all those x bars. So that's your x double bar, mean of the sample means. And then here, for the moment, let's assume that we already know what sigma is. So sigma over square root of n will give you sigma sub x bar. And then we use this formula to develop your upper and lower control limits, where z will be equal to 3 if you desire 99.7% control limits, or it will be equal to 2 if you desire 95.5% control limits. So here is an example. X double bar is 16 ounces, sigma is 2 ounces, and the sample size is 36, and you want 99.7%. So z is equal to 3. Then you apply this into the formula. So let's look at that. Okay, so x double bar is 16, sigma is 2, sample size is 36, right? So sample size is 36, x bar is 16, right? And standard deviation is 2. Now standard error of x bar, so that is your sigma sub x bar. Sigma sub x bar is what? Sigma divided by square root of n. Okay. Now z for 99.7% is 3. If you desire 95.5%, z will be equal to 2. So now the sampling error is z times sigma of x bar. So then the control limits will be, the lower control limit is x bar minus sampling error, okay, and then x bar plus sampling error. Sampling error is z times sigma sub x bar. So that is your, these are your control limits. Of course, for if it was 95.5% confidence you want, you will use z equal to 2. So if you use 2, then these will be your control limits.